Good morning, everybody. So today we shall discuss about one or two applications of ultrasonic measurement system. The first one that we shall discuss is a pulse ecosystem, which is used both for non-destructive testing as well as for biological measurements. The simple pulse ecosystem operates in a time of flight measurement method. So a pulse is launched from a piezoelectric crystal transducer, which is or transceiver. So from that pulse is launched, and then it is reflected at certain boundary, and the reflected one is detected by the transceiver again. And the total time of flight, which basically equal to 2 multiplied by the twice the distance that is from the crystal to the object traveled by the ultrasonic wave divided by the velocity. So it assumes that the velocity is known or constant, throughout the medium. So therefore, it operates on the assumptions of homogeneity of a medium up to certain distance. So therefore, it could be like here we have a ultrasonic transceiver, and then usually it is attached to the medium, because air to medium boundary is quite strong. So discontinuity of the acoustic impedance is quite strong. So therefore, this one is attached to the test medium, which may have several layers. So this is 1, this is 2, this can be 3. Now if some beam is launched here, it will go there. And correspondingly some reflections will come. And also subsequent reflection may come because of the discontinuities. So from here also there is so therefore there would be multiple reflections coming from the various interfaces, interface of medium 1 and 2, medium 2 and 3, and medium 3 and the outside medium, which could be air also. If they are solids, one could be liquid, say 1 is solid, 3 is solid, and 2 can be liquid. So there would be a strong reflections coming from 1 and 2, relatively strong, and also S2, S3, but the strongest reflection that will come from this one, 3 to air boundary. So this is usually operated in pulse mode. The driver circuit is there. This is pulse modulation we can do for the pulse ecosystem, and this is the pulse width. Usually pulse width in ultrasonic pulse ecosystem is in microseconds. From fraction of a microsecond to maybe 1000 microsecond is also available. Systems are available depending on the type of applications and the presence of noise. Generally, this is variable. Pulse width is variable in a pulse ecosystem, and then this is the pulse repetition time. This TW. So generally, after launching a pulse, a counter is started. And from that, the output count can be given to a recorder or display. Now, typically, TR is kept much larger than TW, depending on the thickness of these three materials or the measurement distance. So TR is determined. So this one is L1, distance between medium 1 and medium 2 is L1. Between 2 and 3 is L2. So therefore the first reflection comes from the 1-2 boundary. So this one is TW. The launching pulse, and subsequently after some time the second pulse will come. Then after some time the third pulse will come. However, if there are multiple boundaries like that, so from this point again there will be reflections unless there is some matching fluid is used here. So there will be reflection from this side also, and successive pulses will come. So if I have a matching layer corresponding to the crystal acoustic impedance and the acoustic impedance roughly known from of the medium 1, so then this kind of situation, this kind of reflection will be there. Otherwise there would be further reflections coming out of it. So if there is matching fluid is not there, then subsequent reflections will come. Multiple reflections will be there. And all those reflections will be detected by the detector. However, the fact that every time there is some reflection, it will be multiplied. The strength, that is the height of the pulse or the energy in the pulse, will be multiplied by the reflection coefficient alpha. So the decrease of this pulse width depends on the number of reflections as well as the reflection coefficient. The energy or pulse width, pulse height, of the reflected pulses depends on the reflection coefficient alpha. alpha 2, 3, and transmission coefficient one minus alpha 1, 2. So therefore, from this deflected pulse energy, we can determine the reflection coefficient as well. And if the material 1 acoustic impedance is known, medium 1 or layer 1 is known, then the acoustic impedance of inner layers can be determined. So this is important because outer layer acoustic impedance we can determine by, if we know the crystal acoustic impedance, which is known, and if we do not have any matching impedance, so we can launch a pulse, and the from a distance or even if we touch the crystal here, there will be certain amount of reflection that will come immediately after launching this pulse. So that has not been shown here. So in that way, we can calibrate the acoustic impedance of the medium 1. Pulse repetition rate repetition time PR is kept much higher than TW. So that multiple reflections can be interpreted the logic process unit usually contains either integrator or counters. So this can, or integrator, contains a number of counters. Or and integrators. Usually, how the integrator operates, there is a logic operation is made for every TW. So therefore, for this TW time, the integrations will take place, and that will give some output, either counter or integrator. Then next TW, another counter will start, and then it will reset after some time, after TW. And similarly, it will go on counting this time. So basic resolution is assumed that TW is the resolution of the measurement. Determined by TW. That is equal to TW by 2, because within this TW it takes into account the round trip time. And range of the measurement. Is determined by TR, the repetition time. Now L1 if this time is T1 and this time is T2, the first layer thickness L1 is equal to T1 by 2C1. C1 is the velocity. In medium 1. So C1 need to be known to determine L1, and second layer thickness. L2. So basically the first reflection is here. So twice L1. So L1 by twice L time is equal to twice L1 by C1. Now for the second one, this reflection is coming after the time T1 plus T2. So however here we have just make it T2. So that is T2 by C2. So this system, of course, can also be modified using a frequency modulated continuous wave system. There is a frequency modulated So in this case, so what we have shown here is a single pulse measurement system. So usually if the measurement situation medium is very noisy, so that means this boundary is not very prominent, hazy boundary, and also there are defects in medium 1, medium 2, so there will be a lot of other reflection point or scattering points will give rise to reflection. In that case, this kind of pulse output that we may not get. So this is ideal. Usually because of multi-point reflection and the beam will eventually hit with a beam width. So in practical situations, there will be the practical pulse shape may not be rectangular. So this is due to beam divergence. We have here shown that the beam is going through a straight line path. Actually, the piezoelectric crystal will have a beam profile, so that if I have a target, so there will be a beam profile. So from that, reflections will be coming. Some will be captured by the crystal, some will be, of course, outside. So this beam profile, we have, if we assume a Gaussian beam profile, there will be homogeneous pulse output like this. But usually if there are multiple orientation beam profile, so beam profile could be like multiple maxima. In that case, usually the pulse shaping has to be done or some smoothing need to be done to trigger the counters. Often this measurement is carried out over multiple pulses. So that means one pulse is launched and then we get certain energy here. That is usually done with integrators. There are getting time for the integrators and multiple integrators corresponding to the capability of this equipment, how many discontinuities can detect. Multiple integrators are there, and subsequently what will happen, that first integrator will operate for this time, okay. Second integrator will operate another getting time equal to TW, and then for the next pulse launch, again this integrator one will be opened and the energy will be summed to the previous integrator energy. So like that, the measurement can be carried out in repeated pulse mode. So repeated pulse mode measurements are also available in modern pulse ecosystems. Now we can also do this thing using frequency modulation. So this is driver and oscillator circuit, and then we'll have crystal, and the rest is of course same. Medium is there. So here this oscillator is a voltage controller oscillator, that is a VCO. Which is driven by a ramp circuit. This is the driver signal. This is the measured signal. A multiplier. Bit frequency. F2V converter. Output to the decoder also. So here what happens, we have a voltage control oscillator is driven by a ramp signal. So we will have a frequency variation over certain time. Then while this signal is launched, say it is here, launching time, and the reflected signal is about here. So there will be a frequency shift. And if we multiply this measured signal and the driver signal, because measured signal comes to this multiplier after some time. So that is the time of flight of this. And subsequently, it can also be reflected from that second boundary as well. So that will create a bit frequency after multiplication, which is nothing but the deviated frequency due to finite time of flight. So basically, while it is launched, so it was suppose at the high frequency zone, and then certain time is already elapsed. By that time, the VCO has been driven to a different frequency. So there will be a frequency shift. If we multiply, that component will be picked up and then as a bit frequency, and then that can be frequency to voltage converter, and correspondingly a proportional output to time of flight can be achieved. Typically, center frequency is fixed like 30, 40, 20 megahertz. At multiple of tens, maybe say 10 to 40 megahertz. And the sweep that is the ramp produces a frequency shift of 100 kilohertz or so. So therefore the bit frequency therefore the maximum bit frequency determines the range and the resolution is determined by the resolution of active V converter or in here we can also use some frequency measurement method like spectrum analyzer. Or the resolution of the spectrum analyzer. Now, as we were talking about noisy situation, in noisy situation, using spectrum analyzer frequency measurement would be much more noise resilient than that pulse width time detection method, as in that case, invariably because of the finite beam divergence. Of course, due to finite beam divergence, here also reflection uncertainty will be there. So then the detected signal will not be will not correspond to a particular shifted signal, but a distribution of shifted signals. So in both the cases it is there, but frequency measurement is usually can be done much more accurately than that time detection method. So that's why for noisy and more accurate measurement capable instruments use this frequency modulated method, which is known as FMCW ranging, frequency modulated continuous wave ranging method. So with that, let us stop here for today. We shall